Okay, so today we're doing isotopes and relative abundance. So we've done a little bit on isotopes in the past, but we're going to delve a little bit further into that uh, and have a look at relative abundance and what it is. So our syllabus outcome today is calculate relative atomic mass from isotopic composition. So firstly, make sure you've done your revision questions. They are on page 51. We'll go through the answers. So atoms, they contain protons, neutrons, and electrons. The atomic number is equal to the number of protons. The atomic mass is equal to the number of protons plus neutrons. Neutral elements have the same number of protons and neutrons. Isotopes are the same element with a different number of neutrons. And an ion is an element that has gained or lost electrons. Okay. Now, on to what we're doing today. So why is it that when we've done isotopes in previous lessons, we've used integers for atomic mass. But on the periodic table, atomic mass is usually quoted as a decimal. Okay, so have a think about the reasons, what you think the reason for that is. Now, the actual reason is what we call. Oh yeah, sorry. There's some examples. The reason is what we call relative abundance. Okay. Now, basically, what this is, it's that in a sample um, of an element, there are a very big number of atoms. Now, we'll look into this more in module 2, but the actual number of atoms is on the order of 10 to the 23. So, for instance, 12 grams of carbon has 6.022 by 10 to the 23 atoms. There's a lot, 6 with 23 zeros after it. It's a big number. Now, the element naturally consists of a number of different isotopes in the sample in a specific ratio. Okay, and the standard atomic weight that we display on the periodic table is calculated by using the weight of the isotope and the percentage abundance that it occurs naturally within the sample. Okay. Um, the other thing is at the bottom of the previous page, it had n simplicity. So that's the other thing that we do. We make it a bit simple for ourselves. Uh, each isotope is rarely a whole number. Okay, we simplify it to the nearest whole number just to make things a bit easier on ourselves. But the fact is that protons and neutrons are slightly different weights. Okay, electrons do also have that small effect on weight. So that's another reason why when we actually look at it outside of simplifying it to the nearest whole number, uh, we get those decimals, and we can actually get them in research settings down to 5, 6 decimal places just to be really sure that what we've got is what we've got. Now, an example, so chlorine has two isotopes. We say that they're 35 chlorine and 37 chlorine, and they both have that atomic number 17. 35 chlorine has an actual atomic mass of 34.969. Okay, and its relative abundance is 75.80. 37 chlorine, on the other hand, has an actual atomic mass of 36.966 and a relative abundance of 24.2%. Okay, so basically, what we do we want to then calculate the standard atomic weight. Now, the way we do that is just by using this formula here. So we take the atomic mass, multiply it by its percentage. So you can either do it as a percentage in your calculator. I know the Casio ones can do it. I'm not so sure about Sharp. So times the atomic mass by the percentage, and then add the other atomic mass times by that percentage. Okay. If you don't have the percentage button in your calculator, you just do 34.969 times 75.80 over 100, because that's what percent means. So if you use the percentage button, it just does that divide by 100. And then we do 36.966 times 24.20 over 100. And that should give us the same answer. So that gives us a weight for chlorine of 35.452274. Sorry, I'll go back to that so you can write it down. Now, if you actually have a look at your periodic table, um, specifically the one that you get given with your exams, it quotes the weight of chlorine as 35.45. And so that's how we get to that number. Okay. So we're going to do another example. Using the data in the table below, calculate the standard atomic weight of boron. So you've got a bit of working space there on page 52. So yeah, we got the atomic mass of 10 boron, or boron 10, is 10.013, and its relative abundance is 19.91%. And 11 boron is 11.009 with a relative abundance of 80.09. So do the same thing there. Pause the video, have a go, doing the exact same thing that we just did in the last example, and see if you can calculate the standard atomic mass of boron. Okay, so hopefully you did this for your working out. So 10.013 times 19.91% plus 11.009 times 80.09% should come out at 10.81. Okay, now if we have a look at that, the value given to us on the periodic table of the elements that you get for your exams, we get given 10.81, so that works out nicely. Now another example, this is just another third one. This one's for bromine. So bromine comes from two isotopes, so bromine 79 and bromine 81. So 79 has an atomic mass of 78.92 and abundance of 50.69. The bromine 81 has an atomic mass of 80.92 and a relative abundance of 49.31. So pause the video now, have a go at calculating it, and then come back to the answer in a sec. Okay, so this is the answer here. Again, just the atomic mass times the percentage of relative abundance, plus the other atomic mass times the percentage of relative abundance. Hopefully we get 79.9062. Okay. Yeah, and so that's our relative atomic mass of bromine. Now, if we're given, we may be asked to calculate backwards. So instead of being given the relative abundances and the weights, we might be given the standard atomic weight and asked to calculate the relative abundances from the information that we're given. From the other isotope weights. Now, the way we do that, so here's an example. I'll just take you through the example and you can see how to do it. So use the information below to calculate the relative abundances of the constituent isotopes of copper. So copper has a standard atomic weight of 63.54, but it's made up of two isotopes. So copper 63 and copper 65, and you can see the weights there. Now, the way we go about doing this, we know that the standard atomic weight of copper is the weight of the first isotope times X%. So we don't know what percentage that is yet. Plus the weight of the second isotope times Y%. Again, we don't know what percentage that is at the moment. But what we do know is that because there's only two isotopes, that those percentages need to add up to 100%. Okay. And so what we could say is we can say that Y percentage equals 100 minus X%. And so we can then take this and substitute it in where our Y is. And then that gets rid of the Y component. So it's basically a type of simultaneous equation. Gives us this, okay? So we end up with 63.54 equals 62.95 times x% plus 64.95 times 100% minus x%. Now, remember, when we're expanding brackets, we multiply the thing out the front by both of the things in the brackets. So we end up with this. So 63.54 equals 62.95 x% plus 64.95 minus 64.95 times x%. So what we're going to do is we're going to subtract that so that we get all the x's on one side, all of the numbers on the other side, and then we're going to simplify the coefficients. So we'll do 62.95 x%, take away 64.95 x%, which hopefully gives us this. Okay, so we get negative 1.41 on one side, negative 2x% on the other side. We can then divide both sides by negative 2, which gives us x% as 0.705. Okay, so remember that gives it to us as a decimal, not as a percentage. So our x percentage is 70.5. So remember we moved the decimal point 2 spots. And because y is 100 minus x, gives us our y percentage is 29.5. Okay. Now, if you're not terribly good with maths, come and see me. I'll help you through it. But that's just the basic working of this. Now, getting asked this question might be a bit rare, but you need to know how to calculate it just in case. So we're going to do another example. This time we're using rubidium. So we're given this information, our two isotopes and our relative abundance. So again, we set up the equation like the last one. Okay, so we have our standard atomic mass is our first isotope times x%, our second isotope times y%, and our y% is 100 minus x. So we plug those values in, expand the brackets and simplify. Expand the brackets, then simplify, then divide by negative 1.99, and hopefully we get that as an answer. So x% is 0.73869, so we can round that to 73.9% and 26.1%. Okay, so I'll get you to copy that down. Make sure you're understanding what's going on. Again, if you're not, come see me outside of class time or when you can. I'll be happy to sit down and explain it to you. So, summary for today. So natural elements contain different isotopes. The percentage composition of each isotope is called its natural relative abundance, and that's because it's what occurs naturally. Okay, so these abundances can be different in man-made samples, but we're just talking about nature here. Standard atomic weight is calculated using the isotope masses and the relative abundance, and that's it. So I'll put that back up for us. Make sure you copy down that summary, start doing the questions on page 55. You've got three questions on calculating the standard atomic mass and 2 questions on calculating the relative abundances. Now with calculating the standard atomic mass, probably the one thing that I didn't go further into is the fact that when we get elements with 2 or 3 or 4 different isotopes, we just keep adding them. So there's a question there on page 56 where there's 4 isotopes of lead. It'll just be weight A times A% plus weight B times B% plus weight C times C%, plus D times D%. Okay, so it just keeps adding on like that. So you just do mass times relative abundance, just keep adding them together. Okay, so that's all for today. Have a go at those questions. And if you need any help, come and see me.